Hello friends, I myself Dr. Bharat Parab discussing today with you real numbers. Let us see what are real numbers. See, real numbers. If you take a number line and mark 1, 2, 3, 4, etc. on this number line, if we collect all these numbers in a bracket, these are called natural numbers and are denoted by n as 1, 2, 3, etc. If we add 0 to this and if you collect along with this 0, these are called whole numbers and are denoted by w equals 0, 1, 2, 3, etc. If we extend this line further on the left hand side, -1, -2, -3 will be new members. Then if you collect all these numbers, these are called as integers. Integers and are represented by z, and we collect them as -3, -2, -1, 0, 1, 2, 3, etc. There are still some numbers left in between these numbers, like here it is half, here it is one. These are called fractions. Now the fractions are the numbers which can be represented, which are generally represented in the form p upon q, where p is any integer this and q not equal to 0. Now such type of numbers where integers can also be represented in this form, and p upon q as 1 can be represented as 1 upon 1, -2 can be represented as -2 upon 2, etc. So along with integers and these are and all the fractions, these are called rational numbers. We got the what are rational numbers. Now there are still many numbers left on this number line. What are these numbers? These are irrational numbers. Now let us see what are irrational numbers. Before going to the concept of irrational numbers, called irrational numbers, let us see what is the decimal expansion of fraction. Let us try to solve some more examples. As 7 upon 8, the decimal representation of this will be 8, 7. So 7.88 is a 64. This gives you 6. 8 7s are 54. This will be 4 and 40. So 8 5s are 40, 0, 0. Another example will be 10 upon 3. So this will be 3 here, 10 here. 3 3s are 9, remainder 1. So point 3s are 9, remainder 1. So 3, 9, remainder 1, etc. So these 3 repeats. Yet another example we can see is 1 upon 7, where 7 comes here 1. So 7 1s are 7, will give you 3, 0 here. 7 4s are 28, will give you 2 here. Now 7 2s are 14, gives you 6 here. Now 7 8s are 56, gives you 4 here. 7 5s are 35, gives you 5 here. And 7 7s are 49, gives you 1 here, same as the original one. So in this, if you go ahead solving this or trying to expand this trying to expand this in this, if you see the decimal expansion of this 7 upon 8, the remainder is 0. That means this go to the end, that is terminates. But in this case, this does not terminate, and 3 repeats again and again. We write this as 3 and 3 bar, and we call this as 3 reoccurs. Even in this decimal expansion doesn't go to termination, and this block, we generally call this as block. This block repeats itself. Such type of examples are called non terminating and reoccurring. They always reoccur. So the whole block will reoccur. But if you take examples of this type or some decimal expansions of this type, 1 0, 1 0 0 0, 1 0 0 2, etc., or value of root 2, root 3, root 15, pi, all these values, they don't repeat and don't terminate. Such type of numbers or decimals are called non terminating and non recurring. The numbers which cannot be presented by they cannot be presented by P upon Q form. Their decimal forms are not terminating and non-recurring, are called irrational numbers. So got the definition. What are irrational numbers? Irrational numbers are they are non-terminating and non-recurring. Do these irrational numbers have position on the number line? Yes. Let us see where the root 2 or root 3 or others number lie on the number line. Now let us see whether these numbers root 2, root 3 have any position on this number line. Let us draw a number line like this. 0 here, 1, 2, it will be 1.5, etc. Now let us consider this as 1 unit or 1 centimeter. From this one, draw a segment perpendicular to this at a right angle with same length 1 centimeter and join this triangle. Now, what will be the length of this hypotenuse? By Pythagoras, we get h square equal to 1 square plus 1 square, or h square equal to 1 plus 1 equal to 2, or h equal to root 2. So this is root 2. If you take this as an arc, this as a radius, and draw an arc, this will come somewhere here and touch the line here. So this will be value for root 2. Now if you take another segment perpendicular to this edge and draw a line here with the unit length 1 centimeter and join this to 0 again. Now in this triangle, can you see this? In this triangle, what will be the length of the new hypotenuse h1? This will be h1 square equal to root 2 square plus 1 square, or 2 plus 1 equal to 3, or h1 equal to root 3. That is, now if you take this as radius and draw a arc on a number line, it will touch somewhere here. So this will be the value for root 3. So irrational numbers like root 2, root 3, root 5 all have particular position or definite position on a number line. So these are the parts of the line. Now if you collect these rational numbers, all numbers and irrational numbers, and collect them in a bracket or in a box, these collection of the numbers are called real numbers. So these are called as real numbers. Now let us see what are the uh, certain properties of real numbers and number line. Okay. Now let us see properties of the real numbers. Now let us see the real numbers on a number line. For example, this 2 or root 2. This point represents 2. This point represents root 2. There is no other point on the number line representing 2. That means this point represents only 2. And there is no other number, or 2 cannot be represented by any other point. There is 1:1 correspondence. 1 point, 1 number. Okay, that is one of the property of real number related to number line. Now let us see how to see a number on a number line by successive magnification method. Let us check. Let us check any number 3.217. Okay, this 3.217 on the number line lies on 1, 2, 3, 4. This lies between in these two. Okay, so let us magnify this. Let us magnify this in this way. 3 here, 4 here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 3.2 lies here. 3.217 must be lying between 3.2 and 3.3. So let us magnify this one again. So this will be 3.2, 3.3. So if you see 3.21, 3.22, 3.23, 3.24, 25, 26, 27, 28, 9, 0. So this is be 3.21, 3.22. So this number lies between 3.21 and 3.22. So let us expand this further and again see 3.21, 3.22, and this lies 1, 2, 3, 4, 5, 6, 7, 8. So this is 3.211, 3.212, like that, 3, 4, 5, 6, 7, 3.217. This is the number. So this is called as successive magnification of scale. Okay, and this is how we go to the point where 3.217 lies. Okay, now the properties and the identities of real numbers will be dealt with along with some problems in successive parts of this.